Okay, hello all and welcome to this video where we look at graphing sine and cosine functions. This is exercise 14G from the textbook. There is a link there to an interactive applet online that allows you to see, as you change the angle theta, what happens to the respective cosine, sine and tangent values, and you can actually see on the right that in green, in this case, that's your tangent graph. So as your angle increases up this way, your tangent gets larger and larger and larger. In red is your sine graph, and then in blue is your cos graph. Does it make sense? Cos of 0 degrees is 1, sine of 0 degrees is 0, and it goes on and on from there. And we've seen that when we did the activity in class, where you had to use the unit circle that I provided you and make decimal approximations to plot sine and cos. So let's have a look at, though, that wasn't a very efficient way. That wasn't a very efficient way going, oh, I'm going to actually measure off a unit circle. What is my sine value at 30? What's my sine or cos value at 45? What's my cos value at 60, 90? And go all the way around. That's not very efficient. So what are the patterns? What are the properties of a sine and cos graph that we can use to make sketching really efficient? The first one is that it's going around the unit circle, it's repetitive. Therefore, that means the graph of sine or cos or tan repeats. Okay, it doesn't just stop. It's not like a single, say that's an inverted quadratic or a regular quadratic or a cubic. Okay, it actually keeps repeating, going on and on. If you don't restrict your domain, if you don't restrict how many times you revolve around the unit circle, the graph's just going to keep going on and on in this wave-like motion. So this is the basic graph of the sine, and we assign a couple key things to, or key descriptors to this graph. The first being recognizing what we call a cycle. Okay, so shown here, this full length. So from this point here to this point here is one full cycle. Now what's included in one full cycle? Well, it needs to have this, I guess we'll call it the positive component, and then it also needs this negative component. So for lack of better vocabulary, I talk about it, the graph goes up once and goes down once and returns to the same point. Okay. Now the thing to note is that it does pass through here, but it's only used half a cycle. It's only the positive component. One complete cycle is related to one complete cycle around the unit circle. One full 360 degree revolution. Okay, 360 degree or 2 pi. The thing to note is that we could measure this at multiple different points. Okay, instead of starting at 0, we could start at pi on 2. So from there all the way across to there, to the same matching point, is one cycle. Okay. I could choose 3 pi on 4, and if I go across, not there, but all the way to 11 pi on 4, that is also one full cycle, because the pattern will repeat from then on, because the graph is going down, the graph is going down. So that's an easy way to check if that is actually a repetition point. Does that have the same magnitude, and will the graph have the same gradient at that point? So that's one full cycle. There's a look at one full cycle of the cos graph, which we have seen. You saw in the exercise that you did in class. Same thing, going all the way from 1 all the way up to 1. And this graph, if we continued it, smooth, just keeps repeating and repeating and repeating. So the same thing, from there to there is one cycle. From there to there is also one cycle. Okay. And in all of these cases, for the basic, okay, of cos and the basic of sine, one cycle for a basic graph is always equal to 2 pi, or 360 degrees. So that's how long it takes us to go to revolve around the unit circle. So, when we start to dilate a graph, we can dilate a graph horizontally. Okay, we can dilate away from the y-axis. When we start to do that, well, then the length of that cycle changes. Instead of always being 2 pi, it'll be something else. Okay? We also saw that we could dilate the graph vertically. We dilated away from the x-axis. So that changed the height. It wasn't always one, negative one, the minimum maximum points. So we have some terminology for that. The first one being period. Okay, so that's the set of x values that a trigonomic function takes before it repeats itself. So for basic, I just said that is equal to 2 pi. Otherwise, it's dilated. And then we have amplitude, which is the vertical distance from the middle, okay, so from there, okay, of the function to its maximum or minimum. So how far is that distance up from the middle, or okay, down? Now we know that in the standard basic one, from 0 it's up to 1, or from 0 again -1. So in a basic graph, that is equal to 1. Now the thing to note with amplitude is that is always positive. Okay, we're just talking about how far, okay, not the direction, but just how far is it from the middle of the graph to its tip. Okay, either up or down. Don't care about the direction. If you're doing year 11 physics, you'll know about vectors. So all we're caring about is the magnitude, so the size rather than its sign or direction. So amplitude is always considered positive. So the most basic form is 1, but then we might be dilating the graph so that amplitude will change. It so happens to be that, and we're starting just like gallery of graphs, quadratics, cubics, we're building towards what we may as well call a general equation. General equation where we can recognize certain patterns or certain components of it. If we have a sine n theta, a will actually be our amplitude, and then n will affect our period, where the period is equal to 2 pi on n. So just to put that, our period is equal to 2 pi on n. So it's not just n itself, it's 2 pi on n. And then our amplitude happens to be equal to a. And that's the same for cos. We have our vertical dilation, our amplitude out the front, and then the n inside acts as a horizontal dilation and affects the period. So let's use those two parts of the most basic form of a sine and cos graph we'll identify a couple of them, then we'll move into graphing and how it's helpful for graphing. So if we had 3 sine 2 theta, what's the period and what's the amplitude? Well, the working's out there, but I will go through it. So in this case, A is equal to 3 and our n is equal to 2. So it follows on, our amplitude is equal to 3 and our period is equal to 2 pi on n is equal to 2 pi on 2 is equal to pi. So what does that mean? Just quickly, may as well do a little sketch. It's a sine graph, so it looks like that. What has happened though is my amplitude up to the max now is 3 and -3, and then the time it takes to repeat itself is our period, so that's going to be pi there. And then you could break this down further. You know that this transition point is halfway round, so that needs to be half of our period, so that's pi on 2. And then you could split this further down into quarters if you want to label certain points. But that's the general idea. As soon as you identify the amplitude and the period, sketching becomes much, much easier. Right here. So for each of the following functions with domain R, so that means all real values, so that means the function will repeat on and on and on forever effectively. State the amplitude and the period. Well, A equals 4, N equals 3, so our amplitude is equal to 4, and our period is equal to 2 pi on 3. Pretty straightforward. Okay, in this case, for B, f of t equals negative 2 on 3 sine t on 4. Well, in this case, A is equal to, let's write down the negative 2/3, and n is equal to quarter, because this t on 4 is actually 1/4 times t, so our n value is a quarter, so our amplitude is equal to 2/3. Okay, it doesn't have a sign, it doesn't have the negative sign. That negative sign would actually act as a reflection, like we've seen in all those other graphs. Sticking negative out the front, it reflects it about the x-axis, so flip it upside down, but it doesn't affect the amplitude. So the amplitude is just 2 on 3. Our period is equal to 2 pi on quarter, so our period is equal to 2 pi on 1 times by 4 on 1, so it's equal to 8 pi. So in that case, if the period's 8 pi, that graph is being stretched a lot. Yeah, one full cycle takes 8 pi instead of only 2 pi. For part C, f of t equals negative sine 3 pi t. So A is equal to negative 1, n is equal to 3 pi. So we get our amplitude again is equal to just 1, doesn't have a sign. And then our period is equal to 2 pi on 3 pi, so it's equal to 2/3. So it actually takes 2/3, or we could say 0.66666. And that's still radians, that's still measured, that's measuring in radians. It just doesn't actually have a pi in it, so you need to think, well, compared to a pi with 0.666. So remembering pi is actually equal to 3.14. That's about 1/6, a bit less or a bit more than 1/6 of a pi. Right here, there's some instructions on how to graph on CAS, particularly when you're given a domain. Okay. And just remember, you want to use the this symbol here to put in your domain. So remember that vertical line, that's also called pipe in computer science. Okay. In this case, just means such that. Cool. So graph cos of x such that x is between negative pi and 3 pi. And you can get that such that sign using control equals. So there's some quick notes. Right, this example and the next example have the title using sketching CAS, but I will show you how to do it by hand, and then also there's one more at the end, how to do by hand. So using your CAS, sketch the graph of y equals cos of x for one complete cycle on the axis below. You must also state the domain, range, amplitude, and period of the function. So first off, we have y equals cos x. Our amplitude, or our a value, is equal to 1, and our n value is equal to 1. There is effectively a hidden one there and a hidden one there. So our amplitude is equal to 1, and our period is equal to 2 pi on 1, which is equal to 2 pi, which we recognize as it's just cos x. It's just the standard form.
we could have looked at it and gone straight away, oh, amplitude's 1, period's 2 pi, just to show you that that still works. Okay, so a strategy for all graphing, especially when you're given a grid like this to graph on, is to make your period take a factor of 4 blocks. So your period will be a factor or a multiple of 4 of 4 blocks. I should say multiple, not factor. Okay. So let's see how many blocks I have here. So then how many I can use? So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I have 15. So the biggest whole multiple of 4 I can get is 12. So I'm going to use 12 blocks to make 1 period in this case. Okay, and I only had to fit 1 period. I'm going to go across like that. Now I'm going to count across 12. 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12. And what I make it a multiple of 4 is a sine or a cos graph effectively always has 4 parts. So we have that. So we always have our first part, second part, fourth part, and then there's that third part in there. Okay, so there's always effectively 4 parts to one cycle, and they have nice symmetry. So that's why I block it down into that. I can split those each to have an even number of blocks. It's easy to sort of mark intervals. If that doesn't make quite a lot of sense, that's okay. Just leave it for now. You might start to see it as you sketch a whole bunch more on grids. Okay, so 2 pi, so halfway along will be 6 right there. That's going to be pi. And then half of that will be my peak. Okay, so this point here is half of my period, and then the peak will be at half of the period. Of course, it's halfway along. So 1, 2, 3. I may as well make it there, and then same here. 1, 2, 3. There. And it's a cos graph actually, so I did not pay attention to the question. It's going to be there. 0. So that's x. Oh no, that's not x. Oh my god. Y. That's x. So cos of 0 straight away. 0. That. There we go. That's going to be 1 right there. That's going to be -1. We don't need to actually really do any maths to find these intercepts. If we recognize the unit circle is the most basic form, we can break it down into quarters. Like I said over here, there's 4 parts. So that's a quarter of a period. That's another quarter of a period. That's another quarter of a period. That's another quarter of a period. Okay, so if you know the period, you can always find the distances between each of the key points of the graph. So we have here, that is 0, 1. Here is pi on 2, 0. Here we have pi -1. Here is 3 pi on 2, 0, and here we have 2 pi, comma 1. So this idea of a sine or a cos graph has 4 parts within the cycle is really handy, because once you know the period, you can divide that period into 4, and that gives you, like I've shown, these gaps here. And that's also why you try and sketch where the period is a multiple of 4 blocks. Right here, so that's the graph, but we had to state the domain, range, amplitude, and period of the function. Okay, so the domain, okay, technically of the function. This is interesting. The domain, truthfully, is real, because we aren't given any restrictions just in this y equals cos x. We aren't given a domain. But the fact that it says one complete cycle, we can also say that x is between 0 and 2 pi, one complete cycle. The range, y is between -1 and +1. The period is equal to 2 pi, and the amplitude is equal to 1. And that's a sketch of the graph done. Using your CAS, sketch the graph of y equals -cos x for one complete cycle over the axis below. You must also state the domain, range, amplitude, period, and function. I'm going to go through this one a lot quicker, only because we just did y equals cos x. This is y equals -cos x. Okay, so all the values, okay, have just been reflected. So this graph is much easier to sketch, and if you got it off your CAS, you'd also see pi, that's 2 pi, sorry, 1, 6, that will be pi, will be 3 pi on 2, that is pi on 2. Okay, so reflected down there, -1, key points, there. One trick with sketching cos and sine graphs is at the maximum and minimums, at these almost what you could consider a turning point, is don't start it, and I'll do it here so I don't delete my whole line. Don't start like that. Don't start instantly going up. Okay, technically the graph does go, it's just at that point it is perfectly horizontal, and then starts going across. Okay, just like a quadratic isn't, we don't normally draw a quadratic in a V shape. We come down, we have a nice flat part and back up. Same with sine and cos. We want to have that sort of nice flat part just at the key point. So up the top there and down the bottoms. Same thing for this. Our amplitude is 1. Our period is equal to 2 pi. Domain is, in this case, from 0 to pi, and range is from -1 to 1. So that's 2 simple graphs of cos. Right here, sketch the graph of y equals 2 sine pi x on 6 for x between 0 and 12 on the axis below. Also state the amplitude and period of the function. So in this case, important thing to note is we have a given domain. So that's going to impact our sketching strategies, because we might not actually be sketching now anymore for one cycle. We might be sketching for 2 cycles or 2.5 cycles, 3 cycles. It all just depends how our transformations affect the graph, and then the given domain that we have. Okay, so straight off we have a equals 2, so our amplitude is equal to 2. We have n is equal to pi on 6, so our period is equal to 2 pi on 6, so it's equal to 2 pi on 1 times by 6 on pi, so it's equal to 12. So in this case we were quite lucky that our period is 12 equals 12. So we're just going to have one cycle again. So let's cross, and our period is 12, so I'm just going to use 12 blocks as my period. Six, 8, 9. Okay, it's a sine graph, so straight away we know sine of 0, even when we put in this transformation, sine of 0, pi times 0 is still 0, so equal to 1 times the 2 gives us that. That's going to be 2, negative 2. And sine of 0 is 0. Times 2 is still 0. Not thinking well this morning. Okay, so we have all our points. So it goes down and around. And that is x, and that is y. And that's our graph done. So a key thing at the moment is that we haven't done any horizontal or vertical translation. So this makes it a fair bit easier in that we're taking our sine graph, which is that wave, or we're taking our cos graph, which is that, and we're stretching it horizontally and we're stretching it up and down. That's all we're doing at the moment. So we always know that our sine is going to start like that. Our cos is always going to start up there at 1, or whatever it's stretched to vertically by the amplitude. They're always going to look like that at the moment, and we're just stretching them out horizontally and stretching them out vertically. That's all we're doing at the moment. It's going to get a fair bit more complex than that, because we might have what happens if we had restricted this domain instead to 3. Okay. Well, then you would need to actually substitute it in, and we could have done that too for this, is substitute it in to find where our actual starting point is. So in this case, if we had our change of domain, we'd go, it's equal to y is equal to 2 sine. We need to substitute in our starting point, so we get pi times 3 on 6. So we're getting y is equal to 2 sine pi on 2. Simplifying that fraction, so y is equal to 2 by, and then you need to think, well, what's sine of pi on 2? Sine of pi on 2 is 1, so we're going to get 1, so y is equal to 2. So that would be our starting point, which is what we've got right there. But we wouldn't have any of that. So even though it's a sine, because of the restriction of the domain, it's going to sketch and start looking like a cos graph, just because of our domains actually restricting which part of it we're sketching. So that's just looking forward. This strategy of substituting in points, you can always do that, okay, to get a handle on where your start and finish points are. You may as well. If you're given the starting points, you can substitute them in to find endpoint, and then work within that. Another good strategy. The only other part of exercise 14G, and I apologize, this video has already gone on for half an hour, is identifying transformations or state transformations required to go between one function.
So we might have one function of y equals sine x, and we want to go to y equals 2 sine x on pi. What are the transformations that we need to apply to get a function that reads like that? Okay. And there's a couple of rules that you could do this using the dash method, but with sin and cos, doing dash methods a fair bit harder, so we can do this just through inspection using these rules. If we want to dilate away from the x-axis, we replace y with y on a, where a is our dilation factor. Okay. And if we want to dilate away from the y-axis, so in this case, we're dilating this way, we're stretching it out. In the first case, we're stretching it up and down. Okay, we replace x with x on b, so where b is our other dilation factor. Okay. So an example, say if we have f of x equals 5 cos of x, give the sequence of transformation which takes the graph of y equals cos of x to the graph of f of x. So this question's worded a little bit complex, but it's effectively saying if we have y equals cos of x, okay, what do I have to do to get f of x equals 5 cos of x? Okay. Now, the thing to note here in this, if you remember back to transformations, I'll go to a different color, we have effectively y equals 5 cos of x. This 5 isn't doing anything directly to the x or the y. It's not operating directly on x or directly on y. So we need to rewrite this so that this coefficient is doing something directly to either y or x. So the only way we can do that is turn it into y on 5 equals cos of x. So we can now say, well, what do we need to do to go from y equals cos of x to get y on 5 equals cos of x? Well, that's quite easy to notify that we need to replace y with y on 5. Okay. So what's the transformation? We've replaced y with y on 5. We're dilating by a factor of 5 from the x-axis. That's a little messy, I apologize, with all that other text there. So I might go on to some examples that might become a little bit more obvious as we do an example or two examples. So for each of the following, give a sequence of transformations which takes the graph of y equals sine x to the graph of y equals g of x, which are these two different graphs here. So we're starting with y equals sine x. We're going to something else. What are the transformations that we need to do? Well, the trick here is to rewrite it where the operators are applied directly to the x or directly to the y. So. In this case, the first one's nice and easy. It's already the x, it's divided by 2. That 2 is operating directly on the x. There's nothing sitting out the front here. Don't have to worry about that. So if we started with y equals sine x, to get this, we would have to replace x with x on 2, which gives us y equals sine x on 2. Therefore, in this case, that is we're replacing x, so that's our b, so b is equal to 2. So we are dilating by a factor of 2 from the y-axis. Okay. So the x value is being changed, which means we're stretching away from the y-axis. Part B,
this is where we need to rearrange it, where that any of our numbers are operating directly on the y or the x. So we could rewrite this as y on 3 is equal to sine. And this is interesting. We see 2x, so we instantly think, okay, and this is incorrect, we instantly think, oh, our a value is equal to 2 in here. Okay, but that's not the case. That's not the case. We know n in this case is equal to 2, and we could find our period using 2 pi on 2 equal to pi. But we're not so much worried about our period at the moment as we're worried about the transformation that would give us said period. And we need to recognize that we're replacing x with a fraction, okay, and the actual factor is on the bottom. It's in the denominator. So we need to almost turn this 2x into 2x is equal to x on something. We need to get it in that form. Well, how do we do that? We can write that as, let's get the right color, sorry. We can write that as x divided by a half. By a half. And just to prove that that is correct, if we had x divided by a half, that is equal to x on 1 times by 2 on 1 is equal to 2x. So now we have it in the right form. So how would we get this? This would be by replacing y with y on 3 and replacing x with x on 3. Okay. So therefore in this case a is equal to 3 and b is equal to, no, oh my god. We need to replace x with, I'm jumping ahead. My apologies, I made a couple of mistakes in this video. We're replacing x with x on half. Therefore, my denominator, which is my b value, is half. Okay. Therefore, dilate from x-axis by 3. Dilate from y-axis by half. Okay. And let's think about that dilate from y-axis by half. Because way back at the start, I said, well, 2, that's our n is equal to 2, so it follows on that our period is equal to 2 pi on 2, which is equal to pi. So our normal period of the most basic standard sin and cos functions, the normal period, the normal cycle is 2 pi. If I cut that in half, what's my period now? Well, my period is pi, which matches that with this idea of dilating from the y-axis by half. We're effectively compressing it in. And we're halving everything, or squishing it to half its horizontal length. So that's how you identify transformations required. If you struggled with transformations before in all of the gallery graphs and all those other topics and functions and relations, then clearly it's something you need to go back and review on how you do it via inspection. The videos are up from that chapter, so you can go back and have a look at that, because I did fly through that because it's assumed knowledge at this point in time. If you have any questions, ask in class, shoot me an email, jump on Compass, any of those ways. I'll see you in class. And that's it.